Hello everyone. So for this online lecture, we are going to discuss columns. Now, in the previous lectures, we discussed deflection of beams. So let's say we have a beam, and then we have a force P. The beam could deflect like this. Now, it could deflect by a value of y, and we discussed the equation of elastic curves. Remember your second order differential equation, fourth order differential equation, and singularity functions in order to obtain this value of y. Now for this chapter, we are going to discuss columns or structures that has a force parallel to the length of your beam. So in this case, if we are applying a force P at both ends of our beam, this beam could also deflect this way, similar to the first case right here. But we are going to focus more on the deflection of our columns. Okay, drag it here. Okay. So for this chapter, the ultimate goal is to analyze vertical prismatic members supporting axial loads. What do you mean by axial loads? So let's say we have a long cylindrical sample, which is the blue image here, and we apply a force P, so we pull it at both ends. So we are applying a tensile load. We can first calculate the stress acting on this sample. So its stress is equal to your force divided by your area, and then you will have a certain value. Now, if this value right here, if the stress is greater than your yield, so sigma max is greater than sigma yield, we have a permanent deformation. So we have yielding failure mode if that's the case. Now, let's say we apply a compressive load, which is the second case down here. So again, we have a cylindrical sample. We apply a force P, and the force is along the length of our cylindrical sample. We compress it, and during the compression, there's a chance that this structure here may buckle. Now, you would imagine that the material will first reach yield stress and then it will deform. However, for columns or for longer structures, once we compress our material, before even reaching the yield stress, there's a tendency for the structure to buckle. So for compression, the member can experience failure buckling mode even our stress is less than the yield strength of our material. So the focus of our discussion is going to be on the second case right here, wherein we have a compressive force. Now let's say we have a structure. Now the structure is pinned at both ends. So let's focus on the image on the left side. So we have pinned on the upper part, pinned at the lower part. And we apply a force, which is the blue arrow right here. And then at a certain amount of force, so we go to the right image here, there's a tendency that this structure could buckle, which looks something like this. Now let's imagine the force is P. And this P is increasing, and then once it's increasing, it may reach a critical value wherein your structure will start to buckle. So in this case, if we look at PCR right here, this is the critical force in order for you to buckle your structure. So PCR is equal to pi squared EI divided by L squared. Now PCR, that's critical force or load. Your E is modulus of elasticity. Your I is your moment of inertia. And your L is the length of your structure. Now we are going to discuss more about L because this L will change depending on the ends of your columns. In this case, let's first consider a structure with pinned at both ends on the upper part and on the lower part. Now we have force P. We can also calculate force stress, and this is the critical stress in order to buckle our structure. And if you look at the equation here, that's pi squared E divided by L over R. Now, you know your L is the length of your beam. Your R is your radius of gyration. Now your L over R, just going to drag my, sorry, okay, so I'm going to drag my screen here. So your L over R, so we mentioned that we have P, see R, is equal to pi squared EI divided by L squared. Now we also discussed the stress, a critical stress, which is pi square E divided by L over R squared. Now this L over R here, we can call this one as slenderness ratio. So that's your slenderness ratio. And what do you mean by slenderness ratio? It's the measure of tendency to buckle. Measure of tendency to buckle. Now, that's a measure of the tendency for our structure to buckle. So let's go back to our slide here. So let's look at this plot on the right corner side. Now, we have L over R, and that's the slenderness ratio. And once this is high, you would see that at even lower amount of stress, your structure could buckle. Now, once you lower your slenderness ratio, right here, the amount of stress or critical stress to buckle your material increases, which means you need a higher amount of stress to buckle it, which is good if you're designing your structure. Now, you decrease it, and then until it will reach a certain critical point. Now, note that the buckling takes place before yielding, which means that if you design a structure, it's possible that your buckling, it may happen after your yielding. If that's the case, your yielding will happen first and your buckling will never happen at all, which is the case here. So you see this curve from high slenderness ratio, and then once you lower your L over R, the critical stress increases, which is good, until it reaches a yield point, which is 250, and then now this would be your failure mode, which is based on yielding and not based on buckling. Now, the idea on building your columns is you want your structure to fail more on yield rather than your buckling, because buckling happens at a lower amount of stress. Now, let's go back to our board. So that's two equation for our columns. Now, so we have a force right here. That's our stress. And we know our stress is also equal to P over A. Now, from P over A, so let's say that's your critical amount of stress in order to buckle. We can also define another term, which is R, and that's the same R right here. It's the same R, which is your radius of gyration. That's I divided by A. It's just if you work with this equation, you will end up with this one right here. It's just giving you some of the relationship in order to come up with the final equation right there. Now, how did they derive this equation here? So I'm just going to change it to red. So how did they derive this to equation here? So first, let's look at our structure. So I'm going to go back to this one right here. Oh, before we discuss the derivation of that structure, so let's say we have a rectangular solid structure here, and we applied a force P, for example, which is the blue arrow here, and we push it down, and then you will see that we have two axes of buckling. It's either it will buckle to, on your YY axis, which means it will buckle this way, or it could buckle in XX axis, which is the other way. Now, if you look at this structure, your XX is stronger than your YY, What do you mean by stronger? So if we push this one, this structure downwards, it will buckle more towards your YY, which is the case on the right image right here. So that's your YY axis. So it buckles on YY axis because it's weaker. So which means that if you have this structure, you can predict which way it would buckle. It depends on the strength of your axis. In this case, obviously it will buckle this way. Now, and based on that description, we can say, because it would not buckle in your XX axis, we can say that IXX, and just your moment of inertia, is greater than your IYY. And you are buckling in your YY direction. Again, it's just if you have a rectangular member, which is like this, you apply a force here, you would easily imagine, just imagine a ruler, you hold it at both ends, you push it towards together, or you apply compression force, and it will buckle this way, and it will not buckle towards that way, because again, your XX, you have your XX as stronger axis, and then you have your YY, which is your weaker axis. So, yeah. Now let's go to the derivation of those equations. So we have PCR and sigma CR. Now let's go back to pin connection at both ends of the column. So we have a column on the left side which has a length of L. We have pin A, pin B. We reach a critical amount of P. Your structure starts to buckle, which is the second image here. Now it's buckled. Now after applying a force P, so this is going to be our forces and boundary condition. So we have force P, we have x is equal to 0. So that's our reference point. At x is equal to 0, we don't have any deflection on the left or right side of our column, which means y is equal to 0. Now same thing for B. We have another boundary condition. At x is equal to L, y is equal to 0, which means the position at B, it's at 0 point and it's not deflecting on the left on the right side. Now, in order for us to derive our equation, we need to cut our column. In this case, we can cut it at point Q. And once we cut at point Q, we could imagine that we have a force P acting at that specific point, and then we have our moment at that specific point, and then we can resolve this structure. Now, I'm not going to show the full derivation of this equation, just a little bit. You can check your book, but let's try to derive this one. Just going to, so that you can see the one on the left. Okay. Now at point Q, we can get our moment equation. So we have M. Just going to change the color of my pen. So let's erase this first. Okay. Now, if we look at a structure on the right side, we can see that if we get the moment at Q, there is deflection Y, which means your P creates a moment P times Y. So from this point Q, you have Y, you have force, so you can see that your moment right here is going this way. Which means if I'm going to take my moment at point Q, I can say that my moment is equal to negative Py. Now just imagine that we are applying, let's say, second order differential equation. So from M is equal to Py, we can get this equation right here. P squared y dx squared is equal to m ei, and then we get negative p y e I. So again, it's just applying your second order differential equation to our moment equation. Now, how did we get it? Again, looking on the right side, we have distance y, which, so this p on the top creates a moment as well. So if you sum the moment at point Q, you have your m, you have your p times y, and you will end up with m is equal to negative by. Now, by applying the second order differential equation, we can rewrite this equation as d squared y dx squared plus p over ei y is equal to 0. Now, if you're looking at this equation right here, if you're going to go to your basic mathematics, you will see that you already have y here. You have d squared y, and this is actually your linear homogeneous differential equation, which is second order. We'll put here second order with a constant coefficient. Now, we have this equation. We can set our p squared is going to be p over ei. So we're going to replace this guy right here with p squared. Now we're going to end up with this equation, which is d squared y dx squared plus p squared y is equal to 0. And this equation right here, it's related to harmonic motion. That's related to harmonic motion. Now, if we talk about harmonic motion, so this equation here, the solution for this one, so we're not going to discuss more detail, but if you get the solution for this equation, you're going to get y is equal to a sine x plus b cosine px, and from this equation you can apply boundary condition because you don't know your a and b. That's your constants right there, and in order for you to get your constants, we can apply boundary conditions. So in this case, we can apply boundary condition x is equal to 0, y is equal to 0. So if we're going to apply that one, if we go back to this equation, so your x is equal to 0, so that guy becomes 0. So sine of 0 is 0, cosine of 0 is 1, so this becomes 1. That's 0. You will end up with b is equal to 0. Now you apply the second boundary condition, so x is equal to L. You know that y is equal to 0. So in this case, what you will get is this equation right here. So you know that your b is equivalent to 0, so you're going to end up with a sine pl is equal to 0. So we have your a, you have your sine pl. Now you have two different choices. It's either a is equal to 0 or sine pl is equal to 0 in order for this relation to be true. Now the problem is if we are looking at a is equal to 0 and b is equal to 0, and then we go back to our equation right here, so we know that this equation right here, it's true. Now the problem is which one of this is true. If we go back to our original equation, which is y is equal to this guy right here, if your a is equal to 0, b is equal to 0, your y is equal to 0 at point Q, which is not true. At point Q, so if we go here, at point Q, there's specific y. which means that this guy right here, it's not true. That's wrong. Which means this is the real value. Now that we know that this is the value of your sine PL, which is equal to 0. So let's write that one. So sine PL is equal to 0. Now, this is only true if our PL is equal to n pi. What do you mean by n pi? Your pi, it's 180 degrees. So if you're going to substitute this PL right here, this is only going to be true if you have n times pi. So it's 1 times, let's say, 180 degrees, 2 times 180 degrees. So at those specific angles, this becomes true, which means this is true if our n is equal to 1, 2, 3, and so on. Now, going back to this, going back to our, so now we know that this is our case for this condition. Now remember that p squared is equal to p over ei. Where did we get this one? So when we solve this problem, note that we made an assumption that p squared is equal to ei in order to solve our differential equation. And then from this one, we end up with this one, we end up with this one. So your p, it's really p over ei. So we're going to substitute p squared is equal to p over ei for this equation. So we're going to end up with the following. So, okay. So p squared ei, just going to change the color of my pen. So from here to this point here, so we can get p squared l squared is equal to, again, just imagine you raise everything by 2, so you will get n squared pi squared, and then eventually you're going to end up with p, which is your force, is equal to n squared pi squared ei over l squared. Now, this value right here would be minimum if your n is equal to 1. Note that your n is either 1, 2, or 3, and it becomes minimum at n is equal to 1. Which means that would be the critical amount of force, so we are going to use n is equal to 1. And eventually, we're going to end up with this equation right here, which we wrote earlier, which is p cr is equal to pi square ei divided by l squared. So that's the final equation for determining the critical amount of force to buckle or to buckle your structure. So now we discussed all these derivations right here. You don't have to know all the details right here. I just want to show you how those equations were derived. So again, it's this guys right here. Now that you know the equations are associated with buckling, so I think the next slide would be a problem. So now we have two equations. Again, it's PCR. We also have our sigma CR. Let's go to this concept application. So determine the size of cross-sectional area of the pin-ended column on the left if the column is to safely support A, 100 kilonewtons load, B, 200 kilonewtons load. Use 2.5 as factor of safety in calculating critical load. Your E is equal to 13 GPa. Your allowable stress is equal to 12 MPa. So let's solve that problem. So first, let's change the color of the pen. Now, let's write the given. So we have the length of our column, which is equal to 2 meters. We have E. Oh, sorry. I think it's okay. So your E is equal to 13 GPa. Okay. And then your allowable stress is equal to 12 MPa. And then you have a factor of safety which is equal to 2.5. And we are going to apply the factor of safety to our PCR. Now, and if we go back to the question, so determine the size of the cross-sectional area of the pin-ended column on the left. So our objective is to determine a dimension of that specific column. Now we have those equations. Now for letter A, the condition there is, let's say we have 100 kilonewton load. Now if we have 100 kilonewton load and we have a factor of safety of 2.5, so we can say that our PCR, initially it's 100 kilonewtons, that's our description. However, we have factor of safety which is 2.5, so we have to multiply this one by our factor of safety which is 2.5. We are going to end up with 250 kilonewtons. Now for PCR, we know that the equation for PCR, or the critical load to buckle our structure, is pi square EI divided by L square. Now we are given with E. So we are given with this E. We know what's pi. We have PCR. We have our length. We don't have moment of inertia. However, the question there is what's the dimension? And as you know, moment of inertia is related to your dimension. So first, we can calculate our I. And based on that number, we can assume, for example, that our structure is a square. I mean, the cross-sectional area is a square. So based on our given, we can easily calculate for our I. In this case, we have I is equal to PCR L square divided by pi square E, and that's equal to 250 kilonewtons, which is with the factor of safety. Then we have L, which is 2 meters square divided by pi square. Our E is 13 GPa. So this is 13 GPa. And that's equal to 7.794 times 10 negative 6 m raised to 4. So that's the moment of inertia of our structure. Now we don't have any information, but we can assume that we have a square cross-sectional area. So we have assumed a square cross-sectional area. And if we assume a square cross-sectional area, we know that if we have a square, if this is A right here, we can say that our moment of inertia is equal to A raised to 4 divided by 12. And we know the value of this one, which is 7.794 times 10 negative 6 m raised to 4, which is just this guy right here. Now, based on this one, we can now calculate for the dimension A, which is the side of our square. We'll end up with 98.3 millimeter, or we can say that it's approximately 100 millimeter. Now, our structure now, we can say that this is 100 right here, 100 right there. Now, if we assume a square with 100 by 100, so it's not yet done, we know the dimension. However, if you look at our given, we are specified with allowable stress right here, which means we first have to check if we satisfy all the condition. So given that we assume it's a square 100 by 100 millimeter, so we can check the stress at that specific section if we have P over A. Now in this case, P, we can put 100 kilonewtons, which is our given value without the factor of safety, divided by your area, which is 100 millimeter. Now the area of square is this guy right here, and then you will end up with 10 MPa. Now eventually you will see that this stress right here is less than your allowable, which means it's acceptable. So we can design our structure with this dimension, and then it satisfies the allowable, if we go back here, it satisfies this allowable stress right here, which is 12 MPa. It satisfies everything here, so we can design our structures as a square with this dimension right here. Now going to second question, which is, what if the load is 200 kilonewtons? So we have 200 kilonewtons of load. So if we have 200 kilonewtons of load, again, we can calculate PCR, accounting for factor of safety. So 200 kilonewtons, factor of safety is 2.5. We're going to end up with 500 kilonewtons right here. Similar calculation from before, we can calculate our I, and that's equivalent to PCR L square divided by pi square E, and that's equal to, so I'm just going to write it here, that's 500 kilonewtons. Your L, it's 2 meters square divided by pi square. You have 13 GPa, so you have to be very careful with your units in calculating your or any values in this equation, and then you will end up with 15.588 times 10 negative 6 m raised to 4. Now we have this moment of inertia for our structure, and again, let's assume that we have a cross-sectional area which is a square, so with length of A. Now if this is the case, again, we know that our I is equal to A raised to 4 divided by 12. So using the value of our I, which is this guy here, we are going to end up with A is equal to 116.95 millimeter. Now that's our new design based on 200 kilonewtons of load. Now the thing here is we have to check if it satisfies the condition sigma is should be less than sigma allowable. In this case, let's go back again to our stress. Stress is equal to P divided by A, and our P is 200 kilonewtons divided by our area. So let's say 116.95 millimeter square, and that's equivalent to 14.62 MPa. Now the problem here is your sigma is greater than your allowable. So I'm just going to change it to red. So this guy right here, it's greater than your sigma allowable, which is 13 MPa. So this structure is not going to work. So how can we solve this problem right here? So if we go back to this condition here, we can say that area is equal to P divided by allowable. Let's say we want a critical area in order to satisfy our condition. So we can change this sigma right here into our to a sigma allowable in order to comply with this condition right here. Now if we do that, area is equal to P divided by sigma allowable, and that's going to be equal to 200 kilonewtons divided by 12 MPa. So we're going to end up with 16.67 times 10 negative 3 meters square, and that's going to be your A square, which is for a square cross-sectional area. Now, if you get the square root of that number, you will get A is equal to 129.1 millimeter. Now, that's going to be the design of your structure that will now satisfy both conditions. Now, your question might be, for example, can I just still use this one and then end up with the same thing? The answer is no. The problem here is you have two conditions to satisfy. One is you have factor of safety, and then you have another, it's your allowable. So you have to, in this types of problem, you have to check both. It satisfies the factor of safety that that the problem is specified, and another thing is it also has to satisfy the sigma allowable, which in this case it's 12 megapascal. Sorry, it's 12. I think I wrote it there 13, so I'll change it. So that should be 12 MPa. So yeah, I wrote it 12 right here, so that's correct. So that's how you're going to solve this types of problem. Now we solve this problem and we assume that the connections are both pin-ended. On the upper part, on the lower part, we have pin connections. So what if we have different types of connections? So I'm just going to move this one right here. So we're done with this problem. So let's say we have different types of connections. So in this case, let's say we have a fixed free column. So we have a fix right here, we have a force, and we can also have another type of connection. So we have a letter A, we can see one fixed end. So we have a fixed end, one free end, so it doesn't have any support. You apply a force. It could also buckle. So that's one fixed end, one free end. This is the one we discussed, both ends pinned. So we have pin connections at A, pin connections at B. We can also have a fixed end at the bottom B. We have pin at A, or we can have both ends are fixed. So we have fixed connection at A and fixed connection at B. Now, at these different connections, we can define what we call effective length, L sub E. So if we have this condition, which is A, we can use LE, which is equal to 2L. What do you mean by effective length? So if we talk about, let's look at letter B right here, pinned at both ends. Now, if we are pinned at both ends, you can see that we have this buckled structure here, which is equivalent to L. Now, if we have fixed, let's move to A. If we have fixed at B, we have free end right here. If we apply a force, you would imagine that the shape of your beam would not be exactly equal to B. It's actually half of that, but the effective length is this guy right here, which is LE is equal to 2L. Now, same thing for other support types of support. So we have one fixed end, we have one pinned end. So the effective length that defines your buckling from one point to another, it's 0.7L. If we have a fix at both ends, we have effective length, which is 0.5L. Now you can check the derivations of these values in the book, but once you check the derivations, when you cut your beam, for example, you have to consider all the, for example, the moments created by your support reactions. You have to consider the difference in terms of the buckling mode right here, but eventually you are going to end up with this effective length. And what do we mean by effective length? If we go back to our equation of your PCR, or critical length to buckle, or critical stress to buckle your column, you can change your L into L sub E square, or L sub E, which is right here. So now, okay. So now you have your PCR. is equal to pi square EI. Instead of L, we change now to LE square in order to account for all support reactions. Again, when we did the calculations earlier, we assumed that both ends are pinned. In this case, it's not always the case that it's pinned. You can have a fixed support, free end, and so on. So we now change it to L sub E. Now, your stress critical is equal to pi square E divided by LE over R square. So again, we change this guys right here into L sub E. So let's say if we go back to the problem right here, and then I mentioned that it's not pinned ended at both columns. Let's say both of them are fixed. The only thing that we have to change in terms of calculation is going to change is your L. So in this case, let's go back to our calculation here. So let's say it's not pinned at both ends. You have L right here. So your L becomes L sub E. And this guy, so L sub E is equal to, so if we go back to our lecture, let's say fixed at both ends. Sorry. But fixed at both ends. So LE is equal to 0.5 L. Which means I could change this into LE is equal to 0.5 L. And then everything will be the same. It's just the value of your L. Same, all the calculations will be the same. Of course, if that's the case, probably it wouldn't fit the problem because you're given with allowable. So in case you have a kind of similar problem, you just have to change your L and you should be able to solve this problem. Now again, that's I think the introduction for columns. Our next discussion will be regarding eccentric loading and the secant formula. So thank you and see you on the next lecture.